video, we are going to compute the maximum likelihood estimator for one-dimensional Gaussian distribution. So we are given a set of data points, n data points, x1 through xn, and these are one-dimensional data points. And these are, we'll assume that they are sampled from unknown population with parameter theta. Now, what is the likelihood function? Before defining maximum likelihood estimator, let's define our likelihood function. So likelihood function is basically the probability of the parameter given the observations, which can also be written as probability of x1 through xn given the parameter theta. So the semicolon here denotes that the values x1 through xn are the values of the variable or the observations that we have, and theta is the value of the parameter. And we want to maximize this likelihood function. And the maximization will be over the parameter theta. So our goal is to find a parameter theta that maximizes this likelihood function, or in other words, which maximizes the probability of the observations given that parameter value. Now, maximum likelihood estimator is basically denoted as theta hat for the parameter theta, which represents that it is an estimator of the parameter theta, and this is going to be the argmax theta that maximizes the likelihood function. So the value of the parameter theta that maximizes the likelihood function given the observations. Now let's take an example. So let's consider one-dimensional Gaussian distribution or normal distribution, which is given by the PDF fx as 1 over root over 2 pi sigma square times exponential negative x minus mu whole square divided by 2 sigma square. And this represents the probability density function of the normal distribution. Now here, what are the parameters of the normal distribution? So there are two parameters. One is mu, another is sigma square. So first one is mean and the second one is the standard deviation or the variance of the normal distribution. So again, let's come back to our original problem of computing the maximum likelihood estimator for one-dimensional normal distribution. And the likelihood function of the normal distribution can be defined as follows. It is basically a product of all the probabilities, right, for each of the data points. And the probabilities are given by the PDF for the normal distribution. And we can take a product here because we assume that the observations are the samples that are drawn from an independently, they're done independently from an identical distribution like normal distribution. So they are kind of independent. So that's why we can write them as a product. And then substituting the value of the function f, PDF f, and simplifying the expression, we get, so this can be further simplified into the terms involving summations instead of products, since we have exponential over here, and we can express the likelihood in terms of the exponential of the sums of the terms corresponding to each of the observation as shown. Now instead of maximizing the likelihood, we will take a logarithm of the likelihood function and then maximize this function. Since logarithm is a continuous increasing function, so maximizing the likelihood L will be same as maximizing the logarithm of L. And taking logarithm, we get the following expression. It simplifies the expressions a lot because we have exponential of summation terms over here. Now we have two parameters here for normal distribution. One is mu, another is sigma. So we have to find two different maximum likelihood estimators, one for mu, another for sigma. So let's first try to maximize the likelihood function for likelihood function L to find the estimator, MLE estimator for mu. So for that we have to take a partial derivative of the log likelihood with respect to mu and set it to 0. Since this is going to be a maximum point or critical point. Now that simplifies to the following equation, and which finally boils down to the expression summation I from 1 to n xi minus n mu is equals to 0, from which we find that mu, or the population parameter mu, is basically an empirical mean of the observations. Now let's find the maximum likelihood estimator for the second parameter sigma for the normal distribution. And again we write our log likelihood expression, which is nothing but n over log base e 1 over 2 pi sigma square minus summation of I from 1 to n xi minus mu whole square over 2 sigma square, and which can be further simplified to separate out the constant terms that don't have anything to do when finding the maximum of this log likelihood function. So again we take the derivative of the log likelihood function with respect to sigma in order to find the maximum likelihood estimator for sigma and set it to 0, because at any critical point the derivative of the cost function should be 0. So simplifying, we get minus n over sigma plus, minus half of minus 2 sigma to the minus 3 times summation I from 1 to n xi minus mu whole square. And set it to 0. Again, by simplifying, we obtain n over sigma equals to 1 over sigma cubed summation I from 1 to n xi minus mu whole square, which gives us the value of the maximum likelihood estimator for sigma, which is nothing but square root of summation I from 1 to n xi minus mu whole square, which is nothing but the empirical standard deviation.